In this video, excuse me, in this video, what we want to do is go through, I want to work an example of a Bohr calculation. Okay. Uh, Previously, we looked at, this is the Bohr equation. You'll be given the Bohr equation if we need it for anything. Um, I just want to remember and define some stuff for us. Remember, lambda is our wavelength. H is Planck's constant, so that's 6.626 times 10 to the minus 34th joules times seconds. C is our speed of light, which we're going to use 2.998 times 10 to the 8th meters per second. Both of these ends here are integers. Okay. Our challenge is going to be here remembering that when we're solving this, we want to solve, and if we're solving for wavelength, that this is really 1 over the wavelength, and hopefully I can help us get through that. All right, let's take a stab at this. All right, so what we want to do is we want to find the wavelength of a photon emitted when an electron in a hydrogen atom falls from n equals 6 to n equals 3. Okay, so let's set this up. I have our equation up here. I'm just getting my little video square out of the way. There we go. Same equation as we had on the other side. I'm going to take it. We're solving for wavelength, and wavelength is right here. So we're just going to plug in the numbers and work our way through it. All right. Here we go. Okay. So 1 over wavelength is 2.18 times 10 to the minus 18th joules over H, we said that is 6.626 times 10 to the minus 34th joules times seconds. And C is the speed of light, 2.998 times 10 to the 8th meters per second. All right, there's that piece. This whole dude is multiplied by 1 over n. Final is where we ended up, which was we went from 6 to 3. So final would be 3. And then initial is where we started, which must be 6. Okay. Now, depending on how we feel about working with the numbers, I'm going to just show you how I'm going to work this, right? Our joules cancel out here. The seconds have canceled out. So this thing in the front is all just meters now. 2.18, calculator's making a weird noise. Okay, 2.18 times 10 to the negative 18. Remember, use that EE button. Don't want to do that yet. Okay, so we're going to do this piece by piece. 2.18 times 10 to the minus 18. The joules have canceled. What I'm going to do is multiply the bottom, 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8th gives me 1 point. Crap. Sorry, I'm erasing things I didn't mean to. 1.98647 times 10 to the minus 25. This is meters on the bottom. Okay. Now, this thing is 3. Oh, shoot. These are squared. 3 squared and 6 squared. So 3 squared is 9. So this is 1 over 9. And 6 squared is 36. So this is 1 over 36. Okay. We're just slowly getting our groove on here. Okay. Now we can do 2.18 times 10 to the negative 18 divided by that number we have there is, I didn't hit enter. 10974214.2211. This has units of 1 over meters. You can call it inverse meters, right, if you want to. Remember, this is reciprocal meters because we have reciprocal wavelength is what we're solving for. So there we go. All right, 1 over 9 is a lot of ones. Oops. 0.111111111. Okay, and then 1 over 36 is 0.027777, yada yada. Okay, we'll subtract those two things, this minus that. Okay, so 1097421 1 over meters times 0.0833333, whatever. Okay. We're going to multiply those dudes together. That times, find the number, there it is. That number is 9145117.8518 inverse meters. All right, that is, remember, this is 1 over lambda. So we're not quite done yet. We want lambda by itself. Excuse me. So let's get a clean, well, crap a dog. I thought I had another, I skipped it. Okay, so we're going back to this. I just want a blank slide. Okay. Where did I say? We said 1 over lambda. That's like x. 1 over lambda is 9145117.8571758. That's a 4 inverse meters. All right. So, and I've had students get twisted up in this 1 over lambda business. Okay. So what we have essentially is 1 over lambda is some number. Okay. So if we divide everything by 1 divided by whatever we have, take the reciprocal of it. So 1 over lambda is 1 over n. 1 over lambda is lambda, so this should equal 1 over n. So we're going to take 1 over this number, the reciprocal of our answer. Okay, so 1 over all of this. 9145117.8511758. 1 over meters to the negative 1 is meters, which is why this works out. Okay, so now this is lambda. So we'll do 1 over this. Okay, so lambda is 1.093472 times 10 to the minus 6 meters. All right, that doesn't mean a lot. We like to have our wavelengths in nanometers, so let's go ahead and convert this dude to nanometers. This is our good old friend dimensional analysis here. 1 meter is 10 to the 9th nanometers. So we're going to take this number and multiply it by 1e9 and get 1093.5 nanometers. I guess we'll round this to 3 significant figures for the fun of it, because there's 3 here. That's 4, and those are exact. So this should be 1090 nanometers. Okay. And that should make sense. We're going from 6 to 3. This is going to be a smaller energy transition, so it should have a longer wavelength. All right. We'll work one of these together. You'll probably see it a couple of times. So I'll catch you later.